Okay, great. So our final speaker for today is going to be Arjieet Pal from UCL, and he's going to tell us about frustration and topology in many-body quantum scars. Please go ahead.
Thanks a lot for the invitation to present. It's a pity I can't come to Korea. It would have been great to visit you in Korea, but happy to speak, and let me begin. So first of all, let me thank my collaborators on the two projects that I will talk about. The first part of the talk, or maybe a bit more than the half of it, will be on frustration. And that has been done in collaboration with Hitesh Changlani and Qingmin Lee in Florida State Mag Lab. And the second half will be work done with the members in my group, Jared Jeyaretnam and Jonas Richter at UCL. So this field of quantum many-body scars has taken off in the last few years, largely because of some experimental developments in Rydberg atom chains, where it was observed that certain domain wall initial states take a really long time to relax. So there's some form of, but when you initialize the system in some generic state, the relaxation is very fast. So that was a mystery in some sense when the experiments were done. And it was a mystery largely because this kind of non-ergodic behavior in the absence of disorder was sort of not expected, except we thought only NBL would give rise to this kind of behavior. But at the same time, there were ideas at that time about how even without disorder, one could see some form of non-ergodicity. But now this has become quite an active field, and it's quite exciting to be a part of it. So yeah, and there was a very important work done by our chair and his collaborators, and so they came up with a model which it's an effective model for the experiment called the PXP model. Now it's sort of now well known, and they've discovered these manifold of weakly entangled states in the many-body Hamiltonian, and these weakly entangled states were highly excited states. And what the experiment did, so these were sort of weakly entangled. They could be area law entangled or log entangled, but not volume law with thermal entanglement entropy. So it allows for a wide range of possibilities. And even though this model, for many other sort of measures, one would expect it to be ergodic because it's like level statistics, RGOE, and other such properties could be ergodic. But I mean, there are these manifold of weakly entangled states, and the experimental initial conditions. Experimentalists obviously didn't know about this model, properties of this model before they did the experiment, but the initial condition was cleverly chosen that it largely had overlaps with this manifold of weakly entangled states. And that's why, and the matrix elements between those states were small, and it gave rise to very nice oscillations. And we sort of now understand that phenomena in terms of many-body scars, which is some generalization of the single particle quantum scar idea. But I would like to sort of, at this point, sort of try to broaden a little bit our view of perspective in some sense, and ask there were other papers at that same time which were not addressing this specific experiment, but there were indications that there's some form of weak form of ergodicity breaking, not the strong form of ergodicity breaking, as in MBL could be possible. And obviously it was not put in such, at least maybe so it was not so well studied, but it was the idea, it did exist in some. So there's this quantum East model, which was in the early days of MBL, is a sort of kinetically constrained model, which gave rise to some form of non-ergodic behavior they are observed in these models. And also in this AKLT model studied by Mudgalya et al., they analytically constructed eigenstates of the AKLT model which were violated ETH, and they were not volume law entangled, so they violated ETH. Their phenomenology are different. All these, so this is in this broad class of clean models, disorder-free models, where there are a lot of variable number of non-ergodic states. And I mean, there could be such, so the quantum East model is a model which has glassy dynamics, in which without disorder. So it's like it's analog of structural glasses. An AKLT model has topological order. And part of my inspiration to sort of the title of the talk and the work that I will talk about sort of draws from these bodies of work, which try to connect what we now know of scars and Hilbert space fragmentation in terms of things observed in other models. So yeah, so let me give an outline for the talk. I may not be able to cover all of it, I understand, but let me just put it out there. The first part of the talk will be on frustration. So one of the sort of very well-studied models of frustration is spin models on the Kagome lattice. So corner sharing triangles, many of you are experts on it. I mean, I just started working on it, so I find it extremely exciting. So I will talk about scars and Hilbert space fragmentation in those spin half models on the Kagome, specifically XXZ and its cousins. So three coloring model is a cousin, or one could say, of the XXZ model on the Kagome, and there one can construct exact scars in certain limits, and there are exponentially many of those, and you can sort of move those scars around, and you can perturb away from them and still retain some of the phenomenology, and I'll sort of try to highlight that through the course of my talk. So that will be the first part. The second part, I'll specifically be looking at a model which is again well known, and there are many experts in the audience who have studied this symmetry protected topological model, and trying to sort of find scars in them. And I'll do the course of the talk, I'll say what motivated us to look for scars in these, and how bulk coherence and eigenstate topological order, these are sort of ideas from MBL again, can be borrowed to sort of analyze some of the phenomena here. So yeah, so I mean, it's interesting that it's nice for me to go after Marcello and Alexios' talk, because sort of this, I sort of try to sort of bring together some of the ideas they've already introduced, but also I hope I can motivate some of the parallels that this work develops along with the earlier works. So yeah, so without much further ado, let me talk about the XXZ model on the Kagome. This is a sort of well-known model, corner sharing triangles, spin half. And there was this very interesting point in this sort of parameter regime for this model, which was highlighted in this paper by Hitesh, which is just JZ is equal to -half. And it's some sense, it's a quasi exactly solvable point. I mean, it's a bit of a sort of, it's not exactly solvable. The spectrum is not fully known, but it's still, you know, many properties exactly about this point. And that's why it's sort of solvable. And this model has been studied and has been intensely debated for ground state properties. It's extremely rich. A lot of it is known, much of it is still debated. But the motivation for this work is what happens in excited states. I mean, and is there something that we can understand about excited states by borrowing what we already know about the ground state? So this work focused on the ground state and this exponential degeneracy close to the ground state, but much of that physics is not so relevant to the ground state, and if you tune the model a little bit, it becomes an excited state phenomena, and then one can start asking questions in the same spirit as quantum scars and Hilbert space fragmentation. So just to give you a flavor what this model, where do these special point, where does the idea come from? So at this special point, these corner-sharing triangles, you can split up the Hamiltonian in terms of sort of local terms, and the local terms are projectors. So these are just projectors onto some states, the sort of, which is a sort of entangled states of these three spins, so some form of GHZ states, you could say, in the quantum information language. So you have some projection onto these cluster states, and you have some projectors, local projectors, and these states are basically some realignment of the spins, because the model can be frustrated. So you need to sort of use the quantum nature of the spins to sort of make superpositions of the different spins, and then you can sort of map these states to colorings on the lattice, colorings of the lattice. So this state, which is a equal superposition up and down, is called the red state for that spin, and then this state, which is superposition of up and down with a specific phase, is say the green state, and the other one is the blue state. They are just rotation, 120-degree rotations in the plane. So yeah, so what's the benefit? The benefit is that these states are now sort of the ground state of this projector Hamiltonian. Note that this projector, they're non-commuting projectors, so it's not. So it's these the eigenstates that we'll write down of the full system in terms of this are not mutually orthogonal. So that's complication, but that maybe we can live with that for the time being. So yeah, so one can construct a large number of energy eigenstates at this JZ is equal to -half point by in terms of these red, blue, green coloring. And what that allows us is to construct, so proof, there's a proof of that essentially based on this result by Baxter, that you can, or there are eigenstates, you can construct all the three colorings of the Kagame lattice, so consistent three colorings. So that, what does that mean? That if you have a blue, you can't have a neighboring blue, it has to be red or green. Similarly, so if you have a red, you can only have neighbors which are blue and green. So there are some three colorings of this lattice, and that exists, shown by Baxter et al. And all those states are eigenstates of the system. For this model, these are eigenstates at zero energy. So this is the ground state now. So we're just looking at the ground state, but we'll sort of leverage this to sort of talk about excited states in a bit, but just to give you a flavor of the ground state manifold in this case. So yeah, so here is an example. It's called the Q is equal to 0 state. And then there's a √3 by √3. These are related to what translations you can have in the system. So these are some translation invariant versions. And the number of these three colorings scales exponentially with the size of the system. So, but it's a smaller exponential. So it's exponential, but not as not thermal expectation, not the thermal entropy, and we can't have log 2, for instance. So it's a submanifold of states, exponentially degenerate, and they are, as one would argue, that they are also area of sort of weakly entangled. But one could say, okay, they are ground state, weakly entangled states around the ground state, not so special. But it's very easy to now generalize this to excited states. But before I do that, I mean, there's this is an odd model. The three coloring model is not a very,
Sorry, perhaps I have a very, silly question. Can you go one slide before?
Yeah.
So you say that, these are zero energy states, right?
Yeah, strictly at zero energy.
Okay, how can I see that the energy is always positive, so they are ground state? Is
I
it?
mean, that comes from this projector. I mean, you're just, okay, I mean, you're just projector. I mean, you solve for this local Hamiltonian. You have to solve for this local case.
I see.
And that's just,
Okay. Okay.
those are all zeros, basically.
Okay.
You are sort of creating the configuration which gives zero energy, basically.
Okay.
Yeah, I mean, it's similar to the AKLT ground state in that sense. It's similar, but it's non-commuting projectors. So, I mean, I'll come back to the AKLT kind of models in the second half of the talk where they are commuting projectors. So this is a sort of model with non-commuting projectors. Yeah, good. So yeah, so this is, let me try to hurry up a bit. So yeah, so as you can, so now the Hamiltonian, what is interesting is these three coloring eigenstates, I mean, need not have SZ, I mean, they may combine a lot of SZ sectors as well. They don't have a fixed SZ quantum number, but the Hamiltonian has. So it turns out that if you do the projection of this three coloring state in terms of SZ conservation, in terms of local total SZ, I mean, those are also eigenstates, valid eigenstates of the system. So even though the three colorings are themselves are also valid eigenstates, just that they are linear superposition, and it turns out that those are all at zero energy, so you can do any linear superposition, but then you can now project it down to z is equal to 0, and they remain an eigenstates of the system. So, and there are exponentially many of these eigenstates. So now, so we'll now use this basis of states given in terms of these three colorings, which are exponentially many, to sort of talk about how they can be scars at various different energies. So yeah, so exponentially many exponential manifold at low energies, ETH doesn't apply. At zero temperature, it's but we can easily make it high temperatures, right? How? Because you can just, so as you said, as I showed that that you can have these Hamiltonians as just sum of projectors on these triangles, and you can just pick the coefficients of those projectors to be plus minus. There's no limitation. But the three coloring eigenstates still remain the eigenstates at specifically j is equal to minus j over 2, and we can just, if you choose the number of positive triangles and negative triangles to be equal, then these are at the middle of the spectrum. So where you would expect ETH to apply, but it does. I mean, so now, so it's similar again to the earlier talk that these are zero, in some sense, zero modes. But again, I will show that it is not necessary that these are zero modes, because there's a great deal of flexibility in this sort of term that you can really tune away from it. So yeah, so one can ask, what is the entanglement entropy? So here, this is just at zero energy, because we just chose them to be the positive and negative terms in that way. But we can look at the entanglement entropy as a function of energy. So there are these states. There are lots of weakly as you can see, there are many states. This is now the exact diagonalization of the full Hamiltonian, studying the entanglement entropy for a small system, but still, I mean, there's quite a bit of sort of structure in it. So I mean, but what we are focusing on in this manifold at zero energy, where you get these scarred, I mean, we know what these scarred states are, but you can see that they are sort of not volume or weaker entangled. And they are also not volume law entangled. They are sort of, so they are, once you do the projection onto a specific SZ sector, so total SZ, it becomes log entangled. I mean, and if you start with the pure product state in the three coloring basis, it's strictly area law entangled. So there is some, once you do the projection, there is some extra bit of entanglement, but it's not, it doesn't make it volume law entangled. So yeah, so this is an example of just of the Q is equal to 0 state, so which is which has this translational invariant one. I mean, yeah, so it's without rotation basically. So that state, I mean, you can map it very very well. I mean, you know that analytically. Basically, you can construct that state analytically and show that it's log volume law. So you have these. So by construction, in some sense, you have these ETH violating eigenstates right in the middle of the spectrum. But as I said, you could have SZ projections are also ETH violating. So if you project it to a particular SZ sector, you can violate ETH. We have the same eigenstates. So let's do that. I mean, now we want to split those. So you have this exponentially degenerate sectors, a manifold at 0 energy. You apply a field, it splits those, split those into different SZ sectors. And these are again exponentially degenerate. I mean, each SZ value is exponentially degenerate. So you have this highly degenerate manifold, and I mean, you can even count them. I think these numbers to some extent, I mean, they may not be known analytically, but you can count them sort of efficiently. So you know sort of the degeneracy of these manifolds, and they are exactly degenerate. So the Hamiltonian, where I mean, time evolution of this Hamiltonian is essentially just gives you some phase E minus h times the total spin of that sector, and that's just the action of the Hamiltonian, because the rest of the terms are you have exactly equal to 0. It's this term. We argued that we chose the plaquette energy such that it is exactly equal to 0. So yeah, so you get. So there no surprises.
We have a question from Marcello.
Yeah.
Sorry, I have a rather naive question. I mean, how can you distinguish a log volume scale from a log area scaling if you look at entropies?
I mean, this you can do analytically. I mean, because it's for this 3 coloring. I mean, these 3 colorings you can do that. I mean, it's not so hard.
I fully buy it, but I'm wondering really. Typically this is just a matter of prefactors, right? Prefactor of 2 in your case. Is this correct?
Log which one?
Because if I have log area, I find this log volume very interesting because it also happens for other cases. But it's typically challenging to understand whether this is really a volumetric contribution or it's an area contribution, because if I have L, imagine this is just log L. I mean, I cannot. Do you have an insight of where the?
No, that's a good point. I mean, so you're saying the coefficient of the log, yeah. Okay, so that's a good point. Yeah, I mean, in this case, I mean, you can see that analytically because it comes from. I mean, because all these clusters, I mean, you can count the number of clusters which are contributing to the entanglement entropy, right? I mean, the cut here.
So you are telling me somehow that if I look at the purity will see area versus volume much clearly because it doesn't have.
Yeah. For this class of states.
Okay, thank you.
So one can study the dynamics, and in this case, if you create a state which is in this 3 coloring product state basis, which has superposition on different SZ sectors, I mean, which is you start from a product state, so analogous to the original experiment, you start in a product state in some abstract basis. It's not a simple basis of spin ups and down. It's slightly abstract, but it's still local. And it's a superposition of different SZ sectors. So you get exact Lock-Schmidt echo. I mean, so you can see that this survives. I mean, at this special point. It's at this special point. So you get an exact Lock-Schmidt echo, you get exact scars. And I mean, obviously there are other models which show this. I mean, we're just trying to motivate this from the point of view of the Kagame, XXZ and the Kagame. But what we found that even if you go away from this finely tuned point and stay close to it, j is equal to -½ was the special point, it turns out that these revivals are still very stable, and it's possibly the scars remain stable because, yeah, we can come back to that. I mean, maybe in the latter part. they remain very stable. I mean, we don't see any empirical decay for the largest system sizes, which is not very large, albeit, but usually even for system size, we all do small system sizes, and even in the small system sizes, if there is some very strong effect, I mean, it can survive. I mean, it doesn't, small system size doesn't stop us from at least seeing some general trends. And it seems like this is quite stable. I mean, there's some decay, but otherwise it stays, it keeps oscillating forever. So yeah, so it seems like even at this finely tuned point, there are exact scars, but even away from the finely tuned point, they are quite stable. So that was the main message of this part. But now I will go to slightly modified. Now you have this highly degenerate manifold, and in this highly degenerate manifold, I want to introduce some dynamics in the system. Just this XXZ, we introduce dynamics by putting a field, but are there other ways of introducing dynamics? I mean, putting a field didn't introduce that non-trivial dynamics, it just produced oscillations. But if you introduce sort of now slightly sort of artificial dynamics in this manifold of 3 coloring manifold, say, I mean, you can now introduce dynamics such that you connect to other 3 coloring states. And there's a systematic way of introducing that is by flipping the colorings of, so the red, you can flip the coloring so that red can go to green here and green can go to red. So, and you still remain in the 3 coloring manifold. And you can choose different loop lengths to do that. I mean, you can have, so in this Q is equal to 0, the only loop length which is allowed is this macroscopic loop length, which goes all around the system. But for other states, you can create loop lengths which are different sizes. So 6, whatever, 6, 12, I'll show you some more data. So you can give it the system some dynamics in this scar manifold by introducing such terms. So yeah, so they're like symmetry sectors, and you're sort of connecting states within a symmetry sector. So yeah, so pick 2 colors, pick a 2-color chain, and just flip the colors one to the other, and you get some dynamics. And this is in the same spirit as Rorschach-Kibelson Hamiltonians in quantum dimer models. These also the states, the basis states are not orthogonal, but you can introduce the fluctuating sort of terms in the system, and that dynamics describes, again, Marcello's talk was very interesting because sort of those are the kinds of models which have as some low energy limit some gauge theory, right? So that's an interesting. So this is a motivation to look at sort of slightly more microscopic models. So yeah, so these are called Kempe moves. Those are different. So here is a picture. The moment you introduce this kind of dynamics, the Hilbert space fragments. So now, so as earlier you had these exponential number of scar states which didn't talk to each other. So there were really scars. But the moment you introduce this kind of dynamics, you still retain some of that sort of non-ergodic behavior by fragmenting the system. So they are both connected in some sense. So yeah, so here is sort of, you can sort of enumerate the Hilbert space. So this is some 36-site system in this 3-coloring manifold. You can enumerate all the states. You can ask, if you introduce loop length 6, what are the states which are connected? So the different color legs are the different sort of loop length connections between the 3-coloring manifold. And you can see that there are large parts of the Hilbert space which don't talk to each other. So for loop 6 moves, you have this kind of disconnection. I mean, if you go to loop 6 and loop 8, you connect more states. But for pretty large sort of loop lengths, your Hilbert space still remains fragmented. So these are highly non-local Hamiltonians, but still you do not thermalize fully in these systems. And yeah, so I mean, this is a video, which is pretty, I mean, I find it pretty cool. Is the loop length, this 81-site system, as the loop lengths sort of increase, you get connected, but then you have these clusters which are not connected even at, so there are scars even at very large loop lengths. And this idea, Hilbert space fragmentation, was introduced. Again, there are experts in the audience. So yeah, so this sort of goes from quantum scars and Hilbert space fragmentation within this class of models. So yeah, so I mean, just to get a sense of what the time, how much more time can I have, Chair? If I can cover probably in five more.
Yeah, 5 minutes. That's absolutely fine.
Yeah. So this Hilbert space fragmentation, you can also bring another perspective again from this quantum East sort of inspiration. Is you get a large sort of hierarchical timescales which we associate with glassy dynamics. So in the 3 coloring model, one can see that, I mean, if you take Q is equal to 0 state, so this is dynamics up to probably 6 loop moves. So you introduce dynamics up to 6 site loops, and so you can see the Q is equal to 0 state, which is only allowing macroscopic loops, so that doesn't decay, but other loops decay with different, so you get a wide range of timescales. And that timescale depends on the connectivity of the fragment that loop state sort of sits in. And of course, I mean, we would all love to have some understanding of the general ZXZ model. This is just to highlight that some of it does survive. Obviously, it's not very robust, and that's a question open. It's whether some of this fragmentation, at least some parts of the phase diagram of the ZXZ model, does that play a role in sort of the dynamics of these very interesting models. So yeah, so in the last 5 minutes, let me quickly sort of talk about this other project, which is again related to the earlier talk. And it's motivated again by this AKLT model, but also this result a few years ago by Paul Fendley, where he showed that very vigorously that you can have these edge mode operators, and not just at the ground state, but right throughout the spectrum. So usually you require MBL, at least it was thought that you require MBL or some form of disorder, ergodicity breaking, and that allows these long edge modes to survive. But it can also happen in sort of clean models. You're breaking translational invariance by putting boundaries, but that's a very weak perturbation. But still these edge modes survive. And away from integrability, the proof is for integrable chains, but away from integrability, it's believed that they give rise to pre-thermal edge modes, what's called pre-thermal. So my motivation was that, there are these edge modes which are long-lived, and there are AKLT models which have these scars. Is it possible that these SPT models which have pre-thermal edge modes, so to say, can also have some form of scarring? I mean, so that's what's the motivation. And then we looked at this model, so it's now called the ZXZ model. It's rhyming with PXP. But this is a model on a ladder, and recently there were experiments done on this ladder in Munich. So it's quite experimentally interesting as well. You have these ladders, and these terms in the Hamiltonians are again projectors. You can think of them as projectors on these triangles, but now they're commuting projectors. And so these K terms, and then there is X, which is just some field, and then there's some term which breaks integrability. And lambda is this term, which is the dimerization parameter, which breaks this odd-even symmetry in the system. For gamma is equal to, and V is equal to 0, this is a very integrable model in the sense that every eigenstate is an area law entangled eigenstates, MPS representation. For V is equal to 0 is again straightforward. There are 2 copies of Majorana chains. You can see that ZZ and X gives 1 Majorana and X. Yeah. So it gives 2 copies of the Majorana chain. But what we find is quite interesting, I think, is that even for gamma equal to and v not equal to 0, away from these two special limits, there is some element of non-ergodic behavior if you start from product states in this cluster basis. So here is sort of, if we started from this product state in some cluster basis where the clusters were initialized in some configuration, and you let it evolve. And for this configuration where odd and even sublattices are detuned, it doesn't relax for the longest time, and we believe that it will not relax at all. But if you start from some random configuration of this cluster expectation state with cluster expectation value, then it decays very quickly to the sort of the vacuum state. So now the question is there some, I mean, what we were told by these earlier works on pre-thermal zero modes, that the bulk is actually quite strongly thermalizing. But what I would like to argue that there are actually non-trivial bulk signatures of non-thermalization. So V is equal to 0, again, it's Majorana chain, but it's still sort of a clean model which is delocalized. We find very number of area law entangled states. So, and these area law entangled states, one can think of them, again, drawing the analogy with the AKLT paper, you can think of them as sort of wave-like excitations of this cluster operation, not in the spin basis, but at the cluster basis. So if you create a sort of wave-like excitations by cluster flips, I mean, if V was equal to, gamma was equal to 0, we would have, you can create all eigenstates by such states, but now you can't, and these zero momentum states seem to be a pretty good approximation of some of the states. And even when V is non-zero, we find that this is, okay, it's not so stable for all the states, but there are still some area law entangled states and potentially some log entangled states. And you can put in, and this number indexes how many excitations you're putting in. So you're putting in, for this system size 918 or something, you're putting in some finite fraction of excitations in the systems. So yeah, so what we find, again, you have this kind of scarred manifold. You start with some special product state in the cluster basis, and you only get superpositions from this scarred manifold of states created by the zero momentum, so wave-like excitations. And again, these zero momentum wave-like excitations also have, now you can match, look at the exact ones. So these are the, so by looking at the overlap, find the exact eigenstates which are closest to the wave-like states and ask what their entanglement spectrum is. And it turns out that quite a few of them have pretty strong evidence that they are sort of degeneracies in the entanglement spectrum, which may be a signature of top. And this is slightly tentative, I would say, this signature of the entanglement spectrum, but we are quite confident that if we work a bit harder, we can make that rigorous in some other model, which is slightly tuned away from it. But yeah, but this is already reasonable. Typical state has very, almost no degeneracy, which is this black dots, while the other ones have quite a bit of degeneracy. And the way we understand it is that there is this bulk, because of this dimerization, there is this bulk detuning, that even though the dimerization parameter is actually relatively small, less than 1, you get pretty large, I mean, this is again in the cluster basis, not in the spin basis, and you get pretty large long-lived oscillations between the two. I mean, basically don't connect the two sublattices with this integrability breaking term when you have finite lambda. But if you go to lambda is equal to 1, where dimerization is no longer exists, then you can basically thermalizes like an ordinary system. So this breaking of the sublattice symmetry seems to be important, and then you can have bulk coherence in the system. So anyways, I'll thank you for the time, and I'll just end with these few pictures on the two themes on quantum scars and fragmentation. And thank you for listening.
Thanks a lot. And do we have any questions? Can you go back a few slides to that cluster model? There were like two sets of states, like the red, yeah, one slide after this. So what was the difference between the pluses and the crosses?
So the crosses are states which are constructed by applying. So we know the ground state, yeah. So we can construct all the excited states with the application of this zero momentum operator on the ground state, and that's the entanglement. The crosses are the entanglement entropy of those states, and the pluses are the exact eigenstate which has the maximum overlap with those states.
So this approximation breaks down with V?
Yeah, I mean, at least it seems, I mean, yeah, I mean, it's hard to construct. I mean, yeah, so this I mean, it's hard to say because, I mean, I guess it breaks down at very high excitation energies. I mean, if you put in 8 particles, then it seems like it's still a reasonably good approximation. But if you put in somewhere in between, it seems like it's breaking down, but it works for some low number of excitations.
I guess it's still not even very quantitatively accurate for V0, right? I mean,
well, yeah, I mean, it's not, I mean, I have not shown the overlaps. The overlaps are pretty high. I mean, overlaps would be, I mean, I don't know if I have that. So yeah, so this is sort of some, yeah, so this is, I guess, this is non-zero V. This is overlap of the TJ with the exact ones. And okay, yeah, I mean, it's not, I mean, question is, in a many body problem, overlap of, okay, we didn't get overlap for, it's decaying, yes. It's not,
no, yeah, this looks good, yeah.
yeah, so the overlaps are not so small, I would say. I mean, it's, one would want to be, but it sort of gives us a bit of confidence that, I mean, you take this other state and you take an overlap. I mean, that overlap also seems pretty close to the, I mean, okay, this is exponential. So there's some, yeah, I mean, but the other states are still far from this exact one. So, I mean, yeah, I mean, whether there is a better approximation, it could be that there is a better approximation, better way of constructing this. But I would say it's sort of closer to this, that, I mean, yeah, there may be a better way of constructing it for finite V. But the message is that, I mean, since, yeah, so those are, you can use them exactly to construct all eigenstates in the trivial limit. And there is some stability of certain states away from the trivial limit, even for finite. And yeah. I mean, yeah. I mean, in this case, V is equal to 0. I mean, the entanglement entropy for those states are really areal.
Any other questions? Yeah, go ahead, Alexei.
Yeah, thanks. That's actually more of a remark, perhaps. I wonder, it's related to the first part of the talk, related to the ZXZ model. So how stable are these results? So if you modify the model, I basically would like to point out that, if I understand correctly, there's a recent work by Owen Benton who proposed a generalization of this ZXZ model. So you can, if I remember correctly, you can have a relation between G and GZ, where you preserve the same degenerate manifolds. I'm curious, if you explore this family of models, would you still find the same phenomenology? Would it be different?
Yeah, I mean, I'm aware of the work you are referring to. Yes, I think there would be a similar analogy with those models. I mean, it's not just limited to XXZ. You can construct other models which have similar behavior. And I think we haven't explored specifically the models you are referring to, but our initial, when we looked at it, we thought that they would also have this behavior.
Okay, thanks.
Can you comment on the fragmentation part? So is the pattern of fragmentation similar to the other models that people studied, or do you also get like large as well as small subspaces, or?
Yeah, so this depends on the loop length. This is like a highly dense. There's a large cluster, and then there are smaller clusters, and then there are isolated points. So there's a huge variation in the fragment sizes. We haven't studied the distribution of the fragment sizes in that much detail, but there's
is there some kind of dipole conservation or something like that?
Not in this model. I don't think this has, because it's yeah. I mean, there is some form of conservation law. But it's because we didn't construct it starting from the conservation law. It's hard to see what that conservation law would be. There are exponentially many such clusters that we have checked, that the cluster of the fragments grow with the system. No, they grow exponentially. But what symmetry associates to, it's not clear to me. But there must be some operator which there possibly is some operator which does that.
Any other questions for Arjieet? Okay, I don't see any, so maybe that's a good place to stop the recording. Thanks again, Arjieet. And thanks again to all the speakers of today and to all the participants.